Welcome to the 8A.1 video number 2. Let's pick up where we left off. So we just found the degree, which would be, well, we just found the possible number of real zeros, which is the same as the degree. The next thing we need to find is the actual real zeros, or the real x-intercepts. And so to do that, remember, if you find an x-intercept, that really means that y equals 0. So I would take my original function, and I would replace f of x with 0, again, as something we've practiced, and set that equal to 3x to the fourth minus 6x squared. And then my usual gut instinct is to factor. So if I do that, and I take a GCF of 3x squared out, I'd be left with x squared minus 2. And if I use the zero product property and set both of those equal to 0, I have 3x squared equals 0, and I have x squared minus 2 equals 0. So if I use the zero product property, I first would divide both sides by 3, send them both equal to 0. I'd have x squared equals 0. And here is where the multiplicity thing comes in handy. Because here, if I take the square root of both sides, I technically get x equals plus or minus 0, which means that 0 is an answer twice. So this one has an even multiplicity because 0 repeats 2 times. However, when I solve x squared minus 2 equals 0, if I add 2 to both sides and have x squared equals 2, and I take the square root, I would get x equals plus or minus root 2. So this means I would have a 0 at positive root 2 comma 0 and negative root 2 comma 0. Both of these have an odd multiplicity because the root only happens once, unlike 0, 0, where the multiplicity happens twice. That will all come into play when I graph it in just a minute. The y-intercept is when you set x equal to 0. So if I take my original function, f of x equals 3x to the fourth minus 6x squared, if I plug in 0 for x, that would really be 0 to the fourth is 0, so 0 minus 0. So my y-intercept is at 0, 0, which is the same as the root. Now, if I bring this all together and graph, the first thing I usually like to do is graph where this graph hits the x-axis. So I know there's 3 positions. I know it hits at 0, 0. I know it hits at root 2 comma 0, and root 2 is about 1.4. So it's going to be somewhere in the middle of 1 and 2, a little bit closer. Then I also have negative root 2, which is negative 1.4. So it would be about here. So I know that the graph is going to go through these 3 x-intercepts, and the y-intercept is the same. What also helps me graph this without a calculator is knowing that there are 3 possible turns and knowing that the end behavior looks like this. So that means that my graph is going to start up here. It's going to come down, and because the negative root 2 here only happens once, it's an odd multiplicity. And if it's an odd multiplicity, it goes directly through the graph. And I know that the graph has to turn around because it has to hit 0, 0. 0, 0 has a multiplicity of 2. It happens twice, which means that the graph, on the graph, it's going to bounce at 0, 0. So it would go through negative 1.4, go down, go back up to 0, 0, bounce, come back down. It has to go through this root as well because root 2 only happened once. It's going to go through this again, and then my graph is going to continue upwards. So even though this isn't a perfectly graphed, what I'm looking for, what Schwartz is looking for, is if you understand the general basic shape. Do you understand that the end behavior is both going to the positive infinity? Do you understand that when the roots have a odd multiplicity, that it only occurs once, that it goes through the x-axis, versus if it has a multiplicity of 2 or an even multiplicity, it bounces? That's what we're looking for on a graph like this. Now, again, my graph is not perfect. If you would like your graph to be even more accurate, remember what you could always do is plug in any x value. Like for instance, if this is my original function, f of x equals 3x to the fourth minus 6x squared, if I want to know what happens when x equals 1, I could plug in f of 1 and have 3 times 1 to the 4th minus 6 times 1 squared, which would be 3 minus 6, or negative 3. So I know that the point, plug in 1, get out 3, is on my graph. So 1, negative 3, so that means that if I was being more accurate, my graph should have come all the way down here. So it probably looks more like coming down, up, down to 1, negative 3, and then back up. So my purple one was originally just a sketch, but plugging in any x value you want can help you be more accurate. All right, guys, so this next example, I would like you to do as much on your own as you can. I would like you to find as much of this information. When I unpause, all of my information will be here for you to check, and then together we will graph it. So please pause your video now. All right, guys, so to check in on the information, I got a degree of 5, a leading coefficient of 1, 3 terms separated by a plus or minus. The end behavior, I thought of it as, because it's x to the 5th, I thought of it as an odd function like a cubic. So I drew kind of an odd-looking snake where it's increasing from left to right. So as x goes to the left, the y values go down. So as x goes to negative infinity, y goes to negative infinity. As x goes to the right, y increases to infinity. So as x goes to infinity, y goes to infinity. This notation again is important. Possible extrema, 5 minus 1, or 4 possible turns. Number of real zeros, the same as the degree, 5. The zeros, what I did to do that was I first set the function equal to 0. I then took a GCF out of x. I then noticed that I can continue to factor this piece because x to the 4th is really x squared times x squared. And the two numbers that multiply to be negative 6 that combine to be a 1 technically is a positive 3 and a negative 2. So this is what my factored form was. I set every piece equal to 0. And so I got my first x-intercept to be 0, 0. And it's just x equals 0. So this only happens one time. So it is an odd multiplicity. So in your graph, it goes through the x-axis. X squared plus 3 ended up getting me imaginary roots, so those can't be graphed on the real coordinate plane. And x squared minus 2, the same as the previous problem, I got my two x-intercepts to be positive root 2 comma 0 and negative root 2 comma 0, each of these only happening once, so again there's an odd multiplicity. Just like the previous problem, I got my y-intercept to be 0, 0. So again, if I take all this information and I use it to graph, I'm going to graph my x-intercepts first. This graph goes through 0, 0, and the imaginary roots can't be graphed. But just like the previous example, my roots are at positive 1.4 comma 0 and negative 1.4 comma 0. What makes this different, though, is that we have a different end behavior. We start down and we end up, and we have 4 possible turns this time. So we can go back and check that also. Now, my multiplicity, my roots, I go straight through the x-axis. This time there is no bouncing. So if I start down here with the end behavior suggests, I'm going to go upwards. I'm going to go through this root. I have to come back down and go through this root, go back up and go through this root, and then my end behavior ends going towards positive infinity. So my graph is going to look something like this. Again, this is just a sketch, and that's what my goal is for you. But if we want to be more accurate, let's go ahead and plug in x equals 1 again into the function. So f of x equals 1 to the 5th plus 1 to the 3rd minus 6 times 1. That will be 1 plus 1 minus 6, or negative 4. So the point 1, negative 4 should be on my graph, which would be, so 1, 1, 2, 3. Actually, pretty accurate, I have to say, so that I know that's on there. I could also plug in another point up here just to see, so why don't we do that? What if I plugged in x equals negative 1? So this should say f of 1, by the way, because I plugged in 1. So if I plugged in f of negative 1, that would be negative 1 to the 5th plus negative 1 to the 3rd minus 6 times negative 1. And that would be negative 1 plus negative 1 plus 6, or 4. So the point negative 1, positive 4 should be on my graph. So if I go back up here, negative 1, 4 is here. So if I wanted to make my graph a little bit more accurate, it would come up here and bounce back down to 0 to be a little bit more clear. But that looks great to me. Looks like we went through all of our zeros, and my end behavior is accurate with what we said before. This last example, again, I want to pause and let you try it on your own first. Please notice that there is a negative in front, which is going to change your end behavior. Also, when you get to the factoring is going to be very similar to the problem we just did. So this problem, again, I'm going to pause, and I would like you to do what you can. Even try the graph, and when you come back, I'm going to have it all done and talk through a few things. All right, guys, please pause now. All right, guys, so here's my information. Please take a look to see if you match. Here are the things that I would like to focus on, though. The end behavior, because it is a even power with a negative exponent in front, I knew that it would be like a quadratic and be flipped upside down. So I said as x goes to negative infinity, the y goes to negative infinity. As x goes to positive infinity, the y also goes to negative infinity, which means this would be my end behavior. When I factored, I took out a negative 5 as a GCF. I was left with x to the fourth minus 6x squared plus 9. I noticed that this could continue to factor. X to the fourth is x squared times x squared. The two numbers that multiply to be 9 and combine to be negative 6 is a negative 3 and negative 3. I noticed that both of these parentheses were the same. So when I solved both of them and found the roots, I noticed that positive root 3 and negative root 3 repeated twice, which means that these have an even multiplicity, which means they bounce at the x-axis. And that'll come into play very soon. The y-intercept I got was rather ridiculous, and I got that it's going to be all the way down at 0, negative 45 when I plugged in y equals 0. So if I bring all this information together, my end behavior, it starts below. So I would start my graph down here. I would go up to my root at negative root 3, which is negative 1.73 about. My root bounces because it repeats twice. It has to come all the way down here, go through the y-intercept, probably hit here and bounce back up because it has to go through this second root. It's going to bounce here because it also has a multiplicity of 2. And then my graph is going to come back down, which makes sense because my end behavior is pointing down twice. So this would be a sketch of what the graph would look like. But again, feel free to plug in points. My favorites are 1 and negative 1. So if x equals 1, I would have f of 1 equals negative 5, 1 to the fourth, plus 30 times 1 squared, minus 45, 30. So that would be negative 5 plus 30 minus 45. So that would be 25 minus 45. So I'd have a point at 1, negative 20, which would be probably around here. So my graph seems decently accurate. Okay. So we'll be practicing this in class more tomorrow. I think it's important to be able to interpret this information and be able to graph a sketch. All right, guys, thanks for sticking with me through these videos. Best of luck practicing tomorrow.